Forsyth. I'm a software engineer and community lead at Braintree Payments. We make it easy for you to accept credit cards, PayPal, and other payment methods online and in mobile apps. This talk is about decomposing a highly available Rails app, and these slides, which have no content on them, and the speaker notes, which have all the content, will be on my GitHub page afterwards. So my talk is about what we did to extract a service from the Braintree Payment Gateway. I've got some general tips for developing modern Rails API apps. Then in a little more depth, I'll talk about 3 somewhat unique things that we did during this process that may be useful to you. I'm going to move through this material pretty quickly, and I'll let you decide what you want to hear more about by leaving time for questions at the end. So first, some context. The Braintree Gateway was historically a monorail. The code base dates to 2008 and Rails 2.1, so it is one of the older and larger Rails apps out there. It's on the order of 100,000 lines of code. By 2013, that monolithic architecture was slowing us down. We were limited in our language and framework choice to Ruby and Rails. We had a long ramp-up time for new developers because there was so much to learn just to develop in one app. And the features in that app had gradually become not well separated over time. So we started down the road of decomposition. We started building new features in separate services. We started refactoring the payment gateway to be more modular within a single app. And we started extracting existing features into their own new services. However, we ran into some problems. External facing features still had to be built into the same app because they needed to share one particular subset of the code. And that code is identity management, authentication, authorization, and configuration. Basically, who you are and what you can do. So in 2014, we decided to extract the code that was forcing us to build all new features into the monolith into a new service. Somewhat confusingly, we called it Authy, like the two-factor authentication app, because it does authorization and authentication, among other things. The goal of this project was not for it to really be useful in and of itself, but was to enable more decomposition, allow us to build more new features as their own services and extract more features from the gateway. This was a high-risk project. All of our traffic is authenticated, and so all of the traffic depends on that code. Other people rely on our payment service to be up for their site to function, so we really can't take downtime or risk breaking API authentication. So what was our high-level strategy? I can tell you right now, it was not move fast and break things or anything like that. It was more like move deliberately and don't break things. We wanted really the maximum confidence possible in our code's correctness, and we needed to be able to roll the code out gradually so that we could minimize the impact of the inevitable problems. We were also pretty focused on modernization. I could give a whole talk just on this. The gateway had been updated to Rails 3.2 by this time, but a lot of the code did date back to Rails 2. And the new app was 4.1 from the start. We couldn't use 4.2 because of a bug in Rails. We went from RSpec 2 to RSpec 3 and updated to the more modern expect syntax. We went from 100% custom serialization code to active model serializers. We went from a custom proxy and request queuing layer to Nginx and Unicorn. We used state machines in our code, and we switched from the AASM state machine gem to the state machine gem because transition failure behavior in ASM is not what we wanted and had been causing us problems for a long time, and we were able to get rid of that in the new code. At the time we started the project, we weren't using database connection pooling for everything in the old app, but the new app used PG Bouncer for everything from the very start. We also wrote a fake in-memory version of the entire service in order to speed up and simplify testing, and we use it anywhere that 100% fidelity isn't really important in the tests, where what we're testing are not features related to authentication or identity code. So, of course, we had performance concerns about going from an in-app method call to a network call. Before you cry premature optimization, the optimization was really necessary here. We were 100% sure of that going into it. And we're actually going to need to go through another round of optimization on the same service very soon. I could give another whole talk just on this issue. Of course, our first thought was caching. Luckily, we have some high volume idempotent endpoints that we can safely cache on the client side, completely eliminating the need to make a request at all. Our caching time is pretty short, but it still makes a huge difference for our high volume merchants. And we also are able to do some server-side caching, mostly in Nginx rather than in Rails. So our next thought was about server-side performance, because we knew that our average request time in the old app was not going to cut it in the new app. So we switched to OJ for faster JSON serialization. We used Rails API from the very beginning, which is now merged into Rails, for good defaults and also for significantly faster requests. Most of our requests are in the single-digit milliseconds, and in fact, I believe that most of our requests are in the low single-digit milliseconds. We use Bullet to make sure that our active record queries are sane. We don't have a lot of N+1s. And we did end up writing custom SQL for a couple of high-volume, uncacheable endpoints where we really needed to get things down to a single query and avoid database round-trip times. So our third thought was about connection overhead. The natural thing to do there is to use persistent connections. Unfortunately, this didn't work out super well for us. We found ourselves in a position of choosing between slow server restarts, waiting for the connections to shut down on their own, or dropped requests when we closed the connections unexpectedly. And if we shortened the connection lifetime to the point where the server restart time wasn't a problem, we didn't get as much benefit from it. So instead, we ended up using persistent connections just for idempotent methods, and we actually use a Faraday middleware to accomplish this, and other methods don't use persistent connections. And that way, if the connection is severed, we can always retry because we know it's only being used for idempotent endpoints. The final sort of performance issue that we ran into was very bad performance with large post bodies to this app. And I didn't work on this in too much detail, but basically we had networking issues with large post bodies for some undetermined reason, and just manually gzip compressing and decompressing the post bodies turned out to solve the problem. So these are requests to the new service, not responses from it. So back to code correctness for a minute here. We used all the normal methods of developing confidence in the correctness of our code. First of all, we do TDD extremely heavily at Braintree. On this project, we did a mix of pairing and pull requests, but there were no solo commits on this project. There was at least one pull request code review or a pair on everything in addition to the code review that happens before code gets deployed. We also had a real emphasis on shared context. Even if code had been committed before you get a chance to read it, you still read every single commit that went in, not just on the new service, but in our changes to the old service and any other things related to that infrastructure, everything. We created a seam within the application, then extracted the functionality. This is pretty standard. That way you have an explicit contract when you're building the new service and you're not trying to figure out what belongs where. Once the rollout started, everyone who worked on the project was on the on-call rotation. So we really had shared ownership of making sure things were correct. And we rolled the application out to production long before we were ready to use it for anything real, just so that we could work out any operational problems really early and just sort of get a sense of how it was going to perform. So atelophobia is the fear of imperfection and the fear of never being good enough. And we definitely had that on this project. We decided that all that standard stuff that I just listed, which is very important, was not enough. We still didn't have enough confidence in the correctness of the new service. Because we wanted to rewrite the 6-year-old Rails 2.1 code to make it more maintainable, we had to worry about the quality of the test coverage on that code rather than just copying it over to the new app and updating it for a new version of Rails. But the test coverage, it really wasn't great, and so we weren't confident that new code would be correct even if we copied the tests over line by line. So the very first thing we did to sort of increase our confidence was we wrote a proxy layer, which we called Quackery. It operates at the seam we introduced within the application, not as a separate service. And it's configured with a tree representing the hierarchy of all the endpoints in the old code and also in the new service. And it knows which of those are idempotent. And it allows you to call with a single set of arguments both the old and new code. So this is really important because we wanted our testing to be as close as possible to reality. The Quackery code intelligently calculates the difference it gets from calling both code paths and knows to ignore small diffs in timestamps and automatically generated fields that are going to be different values, and is able to tell us exactly what doesn't match. So this is using real requests we're able to do this. So it's really the ultimate in automated testing because it's not just a test. It really is the actual code that's being used on real requests. In addition, Quackery allowed us to easily switch which code path different routes we're using. So we could toggle things back and forth between the old code and the new code, or both. And when calling both, we could decide which result to trust to make sure that we were saving the result that we wanted to, and so that we could make sure that even after persisting and deserializing code again, or responses again, we were able to get the right answer. Of course, let's come back to our fear of imperfection. We decided that still wasn't good enough. There's lots of non-idempotent endpoints that are sort of less CRUD and more remote procedure call. We wanted more detailed testing than handwritten assertions could really provide on those endpoints too, just like for the idempotent ones. So we said, if we can sort of double read results from these methods that you can call more than once, is there a way that we can double write? Is there a way to do the same thing for the non-idempotent methods? So we decided the answer was yes, but it depends on a dirty little secret that I haven't mentioned yet, which is that the two apps, the new service and the old, we're still sharing a database. Because we have a need for strong consistency here, we can't have two be slightly out of sync or have a copy of the data or anything for the two different services. So they need to be using the same exact database. And once we switch over entirely to the new code, that need goes away, but we needed it while we were rolling this out. So if you Google shared database, something that simple, the very first result is shared databases are an anti-pattern. I won't get into it in detail, but we will talk a little more about the shared database later. But to get back to double writing, because all the state is in that single database, double writing actually was pretty simple. Once we had the code to sort of double read from the idempotent methods, we just added metadata to request to the service so that it could know when we wanted to sort of double call idempotent endpoints that we know when we were also calling them in other code paths. If that metadata is received, you just start a DB transaction before you do anything else on the request, and you just roll it back after the request returns. And suddenly you're able to get the real result of calling that method without any effect on the database state. And you just trust that the other code path made the correct changes to the database state when you called it, which you just do after the one that you've rolled back. So you're no longer limited to double sending to idempotent endpoints. You can now do it to all of our code. You can compare exact results for every single endpoint. Unfortunately, long-running database transactions are a bad idea, and even though most of our requests are really fast, there are certainly some search-type requests that are much slower, in the tens of milliseconds, where we really absolutely cannot be holding a database connection open for that, a database transaction open for that long. And it can really kill your DB performance to do that. I wanted to try it, at least a little bit, in some live environments to see how bad it was, but our DBA wouldn't let me. But even just using the double writing and testing, it lets us check far more state than we can check with assertions, because the entire response from the code is compared to something that we know to be correct. You still can't check quite everything because not all state is serialized back to the client, but it's pretty close. So now let's jump back to the shared database. It's really not acceptable long-term for a lot of reasons, even though it was super useful during the transition for all the features I just mentioned. Once we were 100% using the new service, we really had to split the database. And there's two basic ways to do that without downtime. One is basically add an extra standby to your cluster. Once it's caught up, promote it to a master on a new cluster, basically, and then use the new database from there. The problem with that is that this cluster that this database lived on is very large, even though the database itself is pretty small. And so this would have required us to buy a lot of new hardware at a pretty high expense, and managing more hardware is always bad. In addition, we didn't want this new database to be on a separate cluster. The database really is pretty small. We wanted to keep it on the same cluster and just separate it out. The other method is to just do basically a DB dump and reload. There's a few ways to do this, some of which don't actually involve the dump and reload tools, but it's basically the same thing. And you do this while traffic is paused. It can be either paused explicitly by using something like PG Bouncer, or it can be paused implicitly just because the tables are locked while you're running the SQL statement that does it. There isn't really a good way with Postgres to do this without locking tables and while still maintaining strong consistency between the old and new data. And a combination of the DB size and the DB load and request volume was just too high to do that in the amount of time that we can safely pause things. And the reason we can't do a dump reload while taking traffic, again, is just because we need the new data to exactly match the old data. So if things are being committed while you're copying, you're not going to get that. So we knew from the performance work and the double reading work that most of the high volume endpoints in the new app were idempotent. And in fact, many of them were pure. They had no side effects. They just returned a result. They didn't change database state at all. So it turns out that the non-pure endpoints fell into one of three categories. Either they weren't used for transaction processing, and so we actually could take downtime on them. They're only used by humans who are clicking around in our control panel or by background jobs. And so I'm sort of lied before when I said we can't take downtime. It's really, we can't take downtime for most things, but of course there's always some things that are non-critical. The second category is sort of things like optional auditing and analytics that you can just not do for a little while, and it doesn't really matter. You just have to keep that in mind when you're analyzing your data later. And then finally, there were some endpoints that I'd call nearly pure, where their core functionality had no side effects on the database state, but they did some other things that really fell into that same non-critical analytics auditing type of category. And we could just turn it off for a while without damaging the major abilities to do things like log in or authenticate your API keys. So we added a config option for read-only mode, and when that's enabled, we switched to a read-only database user. This allowed us to just trap DB permission errors and render those back to the client in a friendly way so that it knows that this is just a route that's turned off right now. And then we modified the non-critical and nearly pure endpoints to skip database state changes and just do the things that they could do without changing state. This left us with every single endpoint either working or failing gracefully in read-only mode. So that basically allowed us to use the DB dump and reload method without pausing traffic. The actual op to make that change was pretty complicated, and it did have some issues. We had minutes of degraded functionality for our control panel and where we would be unable to run certain background jobs. But all transaction processing was unaffected, and that was because the app was in this read-only mode rather than down, which is what would have happened had we done a normal DB split operation. That app would have just gone down for minutes, which would have been unacceptable. So that's all I have. Like I said at the beginning, the slides with the speaker notes, which have all the content, will be posted on GitHub, which is github.com/agfor. All right, I think that's all we have time for. If anybody has more questions, just find me afterwards.